Hello everyone, welcome to topic 8.10, buffering capacity. By the end of this, you should be able to explain the relationship between the buffer capacity of a solution and the relative concentrations of the conjugate acid and conjugate base components of that solution. So in this, we're going to look at buffer capacity, and this is a term given to the amount of acid or base that can be added to a buffer system without the pH of that system changing by more than 1. So to increase the capacity of a buffer, so allow it to resist pH change better, you should increase the concentration of the conjugate acid-base pair in the same ratio. This keeps the pH of the buffer the same, but means that there are more moles of the conjugate acid and the conjugate base pair available to react with any acid or base that is added. So there's more stuff to consume, anything that might disrupt the buffer system. So consider the following buffer system, composed of acetic acid and sodium acetate, where the pKa of acetic acid is 4.76. Buffer A has a 0.1 molar of each acetic acid and the sodium acetate ion. If we have 0.05 moles of sodium hydroxide added to the buffer system, assuming no volume change, it reacts with the acetic acid and the amount of the acetate ion increases. And so we see here that by adding that, we see this ratio change. And so when we plug it in here using the pKa of the buffer system, we see that the new pH is 5.24. However, if we use a buffer system that is 10 times more concentrated, right? We multiply this by 10, and we get these both at 1 molar of each acetic acid and the sodium acetate ion, and the pKa is still at the pH here. If we add 0.05 moles of the sodium hydroxide ion, it reacts with the acetic acid again, and the amount of the acetate ion increases once more. So we see those here. So our new ratios are given. And when we plug them in, we see that that is still really close to a 1-to-1 ratio. And the pH reflects that, seeing that it does not change greatly. So we see that the buffer that has a higher concentration of the conjugate acid-base pair, even though the ratio of each to each other is still 1, but because buffer B is 10 times more concentrated for both the acetic acid ions and the sodium acetate ions, it resists change to the pH than the one that was at a lower concentration. Now if we look at a buffer system with unequal moles of the conjugate acid-base pair, so buffer C has a 0.1 molar acetic acid and 1 molar sodium acetate. So the pH of the buffer system when we plug everything in is here. If we add 0.05 moles of sodium hydroxide, we see that the new pH is given here. So the change, or the buffering capacity, like how well it buffered relative, is given there. Okay. If we add 0.5 moles of hydrochloric acid to the buffer system, so in the first one we added the base, in the second one, we added the acid. In the base one, we saw that it reacted with the acetic acid, so the acid in the buffer system. In the second one, we see that the hydrochloric acid reacts with the conjugate base and that the amount of the acetic acid increases. So we see our new ratio here. And then when we recalculate the new pH, it is 5.56, and that the change in the pH is 0.2. Okay. We see that when the buffer system has a greater ratio of moles of the base to moles of the acid, so we have more base than acid, right? It changes less when we add acid. So whichever one is in greater concentration, the base or the acid, that will resist changes to the other component. So if we have base in greater concentration within our buffer system, it'll resist changes to pH when acids are added better than when bases are added, and vice versa. Okay. So buffer systems with greater ratios will resist the addition of the opposite to the system. So they buffer out whatever's in greater concentration. Okay, a buffer is created using 100 milliliters of a 1 molar benzoic acid and 200 milliliters of a 1 molar sodium benzoate. The Ka for benzoic acid is 6.4 times 10 to the negative 5. Okay, our first is calculate the pH for the buffer. Well, using the Henderson-Hasselbalch equation, we need to know, the concentrations, the new concentrations, because we're mixing two different volumes of two different solutions. So we need to know the concentration of the conjugate base and the acid, where the conjugate base is the sodium benzoate, so this is A minus, and the acid, my apologies, is the benzoic acid. So calculating the concentration for the benzoic acid, the new one, okay, this is going to be the one, well, you'll use a dilution equation, so we'll do that. So for our acid in this, remember that the dilution equation is M1V1 equals M2V2, and in this case, M1 is 1 molar, V1 is 100 milliliters, M2 is unknown because we need to find that, and V2 is the total volume, or the new end volume. Okay, so that's going to be 100 plus 200 is 300 milliliters. Okay, because we're combining, we're mixing those into one buffer system. Okay, so solving for M2 in this case, we see that it is equal to 0.333 molar. And so that is the concentration of benzoic acid. Now, if we do the same thing with the benzoate, we see that we do again M1V1 equals M2V2, where M1 is 1 molar again. V1 is 200 milliliters. And then M2 is our unknown, and V2 again is 300 milliliters. And so our M2 for the conjugate base, or concentration of our conjugate base, in this case is 0.667 molar. So now we know the concentrations of our conjugate base and acid pairs for this system, so we can plug it into our Henderson-Hasselbalch equation, remembering that Ka is given, so if we take the negative log of the Ka value, we get pKa, and then we're going to add that to the log of the concentration of our benzoate ion divided by the benzoic acid concentration. When we plug this in and solve using a calculator, please use a calculator. My brain hurts thinking about that. You should get a pH of 4.49. Okay. Then B, will the pH of the buffer change more when acid is added or when base? We will look at the one that is in higher concentration, and that is the conjugate base of the buffer system. So since it is like higher concentration of the base, it'll resist acid addition. So it'll change, it will change less with the addition of an acid. My apologies. It will change more with the addition of a base. And this is because the acid in the buffer system is at a lower concentration. Okay, so now we're going to look at the we do together. 3 buffers were created using weak acid with a pKa of 3.2 and its lithium ion conjugate base. And they are given buffer X, Y, and Z with the following data. What is the pH of each buffer system? Okay, so we are going to assume, since they are all in 1 liter, that these are our concentrations as well. Okay, so for X, there's not a lot of room here. We see that pH is equal to pKa. Our pKa is given as 3.20 for every single buffer because they're all the same acid, plus the log of the concentration of the conjugate base, so that's 0.5 over 1. And when we plug that into a calculator, we should get 2.90. I want you to try this for Y and for Z. Please pause the video now and try this with Y and Z. Okay, for Y and Z, you should have seen that they both of those buffers will have a pH of 3.50. Granted, the ratios are different of the acid to its conjugate base, but they both are at 3.50. Okay, which buffer will be best at resisting the change to pH when acid is added? Well, for adding acid, we're going to look for the one with the highest base concentration, because that'll resist the change better than anything else. Well, that'd be the conjugate base, and that would actually be Z, because it has 4 moles of base per every 1 liter. So our answer is buffer Z, because its conjugate base is highest. Okay, so that concludes these notes. Please complete the you do, check your work, and thank you for tuning in.